Hi, my name is Sarah Zuderman and the date is August 14th of 2021. Today we will be going over the Unit 4 case connections, and the first case that I chose is case 1, and this concerns a newborn girl who appeared normal at birth, but within 24 hours she developed lethargy, hypothermia, and apnea, and she also was ordered a blood workup which revealed high ammonia levels within the blood. And so in our first question, we were going to discuss the normal mechanisms of ammonia transfer within the body, and we're also going to discuss the role of transamination and how nitrogen transport is connected to gluconeogenesis in the fasted state. So, to begin, ammonia is a common element found within the body that is required for the synthesis of complex proteins and other complex molecules. Ammonia is released within the body through transamination and the degradation of amino acids. The accumulation of ammonia within the bloodstream can lead to serious health problems, including brain damage, coma, and even death. Studies have shown that ammonia is toxic to the brain and inhibits glial cells' ability to excrete potassium. With potassium accumulation in the brain, the defenses against ammonia are disabled, further compromising brain tissue and causing seizures and coma, etc. Ammonia is not soluble in water and cannot be excreted through the urine, so it must be transported to the liver to be converted into urea. Urea is a soluble compound and is able to be transported to the kidney for excretion within the urine. Ammonia transportation through the body is accomplished through various mechanisms. First off, in a fasted state, when there are limited resources for energy, cortisol is released. Cortisol activates skeletal muscle protein catabolism for the use of energy production. The initial metabolism of amino acids begin with the dissolution of the amino acid from the carbon skeleton. This happens through a process we call transamination. The remaining carbon skeleton is utilized in the production of glucose through gluconeogenesis. And almost all of the carbon skeletons that are produced through transamination are able to be used in glucose production, exempting ketogenic amino acids, which are metabolized to acetyl-CoA. On the other hand, the amino acids that are used for gluconeogenesis are termed glucogenic. Glucogenic amino acids are metabolized to an intermediate of the tricarboxylic acid cycle, otherwise known as the TCA cycle. For example, phenylalanine is first converted to tyrosine by phenylalanine hydrolase, and phenylalanine and tyrosine are both different types of amino acids. Tyrosine can be transaminated to homogeneous state, which can subsequently be catalyzed by homogeneous state oxidase to generate intermediates for the TCA cycle. These intermediates include fumarate, which is used directly in the TCA cycle, to acetoacetate, which requires conversion to acetoacetyl coenzyme A, and then to acetyl-CoA before utilization in the TCA cycle. The TCA cycle intermediates are ultimately converted to glucose in the process of gluconeogenesis, therefore relating nitrogen transport to gluconeogenesis. Transamination is the transfer of ammonia from an amino acid to an alternative keto acid and requires the cofactor pyridoxal phosphate. In the example of pyruvate, transamination creates alanine, which is a non-toxic carrier of ammonia. Alanine is safely transported in the circulatory system to the liver, and then once alanine arrives at the liver, it is again transaminated, but this time it's back to pyruvate. Pyruvate can then be utilized in gluconeogenesis, providing another relation between nitrogen transportation and gluconeogenesis in the fasted state. Transamination transfers alanine's ammonia to alpha-ketoglutarate, synthesizing glutamate. Glutamate is deaminated by glutamate dehydrogenase and releasing free ammonia to be used in the urea cycle. Another non-toxic transporter of ammonia is glutamine. Glutamine is synthesized by glutamine synthetase through fixing free ammonia to glutamate. Glutamine synthetase is found in peripheral tissues and acts as an ammonia detoxifier, preventing the harmful accumulation of ammonia. Glutamine is transported to the liver and deaminated by glutaminase, freeing ammonia for urea production. So within the case, further analysis shows that urine orotic acid levels were markedly elevated and the plasma citrulline level was normal. So now we are going to look at which enzyme is most likely to be deficient within the urea cycle and which enzymes are least likely to be impaired. So considering the accumulation of ammonia in orotic acid, the most likely urea cycle enzyme to be deficient is ornithine transcarbamylase, or OTC. OTC is an X-linked disorder and is the most common type of urea cycle disorder. Mild OTC is characterized by sudden fatigue, poor appetite, headaches, migraines, forgetfulness, trouble focusing, difficulty with learning, and gastric upset subsequent to the consumption of proteins. Severe OTC is characterized by catastrophic hyperammonemia, developmental delay, seizures, psychiatric disturbances, cyclic vomiting, and even death. The urea cycle begins with the combination of ammonia and carbon dioxide by carbonyl phosphate synthetase 1 to generate carbamyl phosphate. Catalyzed by OTC, carbamyl phosphate is combined with ornithine, which synthesizes citrulline. Citrulline would then be shuttled out of the mitochondria and go through two conversions in a cleavage to be excreted as urea. In the incidence of OTC deficiency, carbonyl phosphate cannot be used in the urea cycle and is alternatively shuttled to the systole. In the systole, carbonyl phosphate is used as a substrate in the synthesis of orate, an intermediate of pyrimidine synthesis. Accumulation of orate, otherwise known as orotic acid, as seen in the patient described above, is a characteristic of OTC deficiency. Inactivity of the urea cycle subsequent to OTC deficiency inhibits urea production and successive excretion through urination. Absence of urea production traps ammonia within the body, termed hyperammonemia, as seen in the patient described. Alternative deficiencies in the urea cycle are unlikely due to the accumulation of carbonyl phosphate and subsequent orotic acid, as seen in the patient described above. A deficiency in CPS1 is illogical due to the presentation of elevated orotic acid. Orotate requires the intermediate carbonyl phosphate for synthesis. Without CPS1 synthesizing carbonyl phosphate, the intermediate will be non-existent within the mitochondria. CPS2, however, is active within the systole, synthesizing carbonyl phosphate and subsequent orotic acid. In spite of orotate synthesis, orotic acid does not accumulate due to pyrimidine synthesis, which requires orate as an intermediate. CPS2 is also regulated through products of pyrimidine and purine metabolism to ensure that overaccumulation of carbonyl phosphate and orotate does not occur. Hence, overproduction of carbonyl phosphate and orotate is not possible within CPS1 deficiency, barring no complications with pyrimidine synthesis. Therefore, due to evidence of elevated orate, CPS1 is the least likely enzyme to be deficient. Deficiencies in arginosuccinate synthetase, arginosuccinate lyase, or arginase are unlikely due to accumulation of orotic acid, which is synthesized with the accumulation of carbonyl phosphate. A deficiency in any of these three enzymes would result in the accumulation of their respective substrates, not orotic acid. For example, in arginosuccinate synthase deficiency, there would be an accumulation of the substrates aspartate and citrulline. In the profile above, citrulline levels are normal, negating the possibility of a deficiency in arginosuccinate synthetase. On the other hand, a deficiency of arginosuccinate lyase would cause an accumulation of arginosuccinate due to insufficient catabolism, not orate again. Lastly, arginase deficiency is characterized by an increase in fumarate, arginine, and subsequent N-acetylglutamate. N-acetylglutamate is an allosteric activator of CPS1 and is enhanced by arginine. Therefore, an accumulation of arginine would enhance flux through the urea cycle, although with insufficient arginase, this would lead to further accumulation of arginine, which is not seen in the patient described above. And the last question they have here is which amino acid, if any, becomes essential as a result of this deficiency? So, as I stated, as a result of OTC deficiency, arginine becomes an essential amino acid. Arginine is produced in the final steps of the urea cycle, and deficiencies in OTC negate the possibility of arginine production through inhibition of citrulline production and subsequent reactions within the urea cycle. Therefore, arginine must be supplied through an outside source, such as through the diet or supplements.